Okay, let's dive right in. Today, we're embarking on what I can honestly only describe as a cosmic detective story. I want you to imagine we're looking at the entire universe through the lens of a weary investigator staring at a massive, chaotic caseboard. We've got our neatly closed cases, those beautiful moments where the scientific method triumphs spectacularly. We've got our frustrating cold cases, where the usual suspects just keep slipping through our fingers, and, perhaps most excitingly of all, we have our active breaking crises. I'm talking about the kind of anomalies that are literally shaking the very foundations of modern astrophysics right now as we speak. So if you love a good mystery, well, you are in the exact right place for this explainer.
Let's start by opening up our first major closed case: gravitational waves. When Albert Einstein predicted these literal ripples in the fabric of spacetime way back in 1916, using his brand new theory of general relativity, he knew they'd be small. But he actually thought they would be so infinitesimally minuscule that humanity would never, like literally never, be able to build a machine sensitive enough to detect them. For decades, it really seemed like he was right. Catching one became the ultimate, seemingly impossible holy grail of experimental physics.
It took a full century of agonizing patience for this science to actually pay off. Think about that timeline. In 1916, we get the mathematical prediction. Jump to the 1970s, and astronomers finally spot a binary pulsar system losing orbital energy at the exact rate predicted if it were radiating gravitational waves. Which is a brilliant indirect clue, sure, but it was still just circumstantial evidence. Finally, on September 14, 2015, the LIGO observatories recorded GW 150914. This wasn't just some tiny theoretical wave. It was the violent, cataclysmic merger of two incredibly massive stellar black holes. Finding this was a monumental, historic triumph for the scientific method.
To truly appreciate just how massive this triumph was, we really need to consider the sheer, mind-bending absurdity of what was actually measured. As those two black holes collided, they sent a ripple through space-time that washed completely over Earth. It stretched and squeezed the 1,120-kilometer effective span of the LIGO detectors by 1,000th of the width of a single proton. I mean, let's put that into perspective. That is proportionally equivalent to measuring the distance to the nearest star outside our solar system, Proxima Centauri, and somehow noticing that the distance changed by the width of one single human hair. It's just unreal.
And yet, while the signal was impossibly faint here on Earth, the event that caused it was nothing short of apocalyptic. The peak power output of those merging black holes in their final milliseconds was 3.6 times 10 to the 49th watts. That number is staggering. It's almost incomprehensible, right? For a fleeting fraction of a second, that collision radiated more energy than the combined light of every single star in the entire observable universe. Catching this incredibly faint cosmic whisper from the most violent event imaginable firmly, undeniably closed the book on Einstein's last unproven prediction.
So, with Einstein's final prediction perfectly closed, we move to the ultimate cold case: the evasive hunt for dark matter. Now we know there is an undeniable, massive gravitational presence holding our galaxies together, but its actual particle nature has completely eluded direct detection. It is, for all intents and purposes, the ghost haunting modern physics.
Whenever a case goes cold, some investigators inevitably start questioning the fundamental assumptions. Is dark matter even a particle at all? Or do we just fundamentally misunderstand how gravity works on a large scale? This debate pits modified gravity theories directly against the dark matter hypothesis. But independent, high-precision constraints from the Milky Way's own dynamics are rapidly closing the door on modified gravity. When we analyze the Gaia satellite's data on exactly how stars spiral and rotate in our galaxy, modified gravity theories show severe structural inconsistencies. They are disfavored by over 13 sigma. Just as a reminder, in physics, a 5 sigma result gives you a 1 in a million certainty, so 13 sigma, that essentially slams the door shut and locks it. Meanwhile, an invisible dark matter halo naturally and perfectly explains all these intricate mechanics. The ghost is real, we just desperately need a new way to catch it.
Which brings us to a wildly innovative new approach. People are asking, if dark matter only interacts via gravity, why on Earth are we trying to detect it using other fundamental forces? Instead, theorists are proposing an array of quantum-limited mechanical sensors. Picture basically a vast grid of microscopic suspended pendula. Instead of hoping a dark matter particle magically bumps into an atomic nucleus, scientists want to use this mechanical array to track ultra-heavy dark matter purely by the tiny gravitational tug it exerts as it flies through the sensors. It's exactly like tracking an invisible subatomic particle leaving a trail of bubbles in an old-school bubble chamber.
This step-by-step physics here is just absolutely fascinating. First, you deploy a massive macroscopic array of hundreds of millions of gram-scale impulse sensors. Second, you just wait for a passing, ultra-heavy dark matter particle to streak through the array at roughly 220 kilometers per second, exerting a tiny transient Newtonian gravitational force on the nearest sensors. And the third, and obviously hardest step, you have to use incredibly advanced techniques to evade quantum measurement noise and thermal noise so you can isolate that one correlated track. It requires zero assumptions about non-gravitational physics. It's pure, unadulterated gravitational direct detection.
Now, while theorists are redesigning those mechanical arrays, observers have been scanning the skies for indirect signs of dark matter annihilating itself. And nowhere is a better target than the galactic center, where dark matter should theoretically be the thickest. But here is where we hit an active investigation totally filled with red herrings. The center of the Milky Way is the most crowded, complex, and obnoxiously noisy neighborhood in our entire galaxy. It's the cosmic equivalent of trying to hear a specific person whisper in the middle of a heavy metal concert. It is an absolute breeding ground for false alarms.
Case in point, a few years ago, the Fermi Gamma Ray Space Telescope detected this bizarre, unexplained glow of high-energy light radiating straight from the galactic center. This sparked immense excitement. Could this finally be it? I want you to ask yourself this question. Is this Fermi Gamma Ray excess truly a signature of weakly interacting massive particles, WIMPs, crashing together and annihilating into pure energy? For a brief, wonderful moment, the astrophysics community thought we might have actually cracked the cold case.
But let's look at where the evidence actually leads us. The WIMP dark matter theory requires a very specific, perfectly spherical distribution of dark matter at the center of the galaxy to create this exact glow. But recent, better mapping shows that the gamma ray excess isn't a sphere at all, not even close. It perfectly matches the asymmetrical X, or peanut-shaped distribution of old stars, specifically millisecond pulsars, sitting right inside our galactic bar. The light is tracking where dead stars live, not where invisible dark matter clusters. The evidence is overwhelmingly pointing away from dark matter here, making this yet another frustrating but illuminating dead end. Okay, this brings us to the most thrilling part of our explainer, the breaking crises. These are the current, highly active cases that are keeping cosmologists awake at night. We're moving way past just missing matter to fundamentally questioning the age, expansion, and evolution of the entire universe, and it's all driven by two massive anomalies: the Hubble tension and the mind-bending mysteries of the cosmic dawn.
The Hubble tension is basically a fierce, ongoing disagreement about exactly how fast the universe is expanding. If we look at the early universe using the cosmic microwave background, our best models predict a relatively slower rate of expansion today. But when we measure the present-day universe by observing pulsating Cepheid stars, which act as these great cosmic mile markers, and supernova, we get a significantly faster expansion rate. Remember that 5 sigma certainty we talked about earlier? This disagreement is greater than 5 sigma. There is literally less than a 1 in a million chance this is just a statistical fluke. Our two absolute best ways of measuring reality are fundamentally clashing.
And if a broken expansion rate wasn't enough to give astrophysicists a headache, the James Webb Space Telescope recently peered back into the cosmic dawn, the very infancy of the universe, and found objects that appear way too massive, way too bright, and far too mature to exist so soon after the Big Bang. But here is where things get absolutely wild. There is a thrilling new theory that bridges everything we've talked about today. JWST might not be seeing early galaxies at all. What if JWST just found a black hole star hiding in plain sight? Theorists suggest these insanely bright objects could actually be supermassive dark stars. These wouldn't be powered by normal nuclear fusion, but by the literal annihilation of dark matter in the early universe. The dust hasn't settled on whether we're looking at bursty star formation or invisible dark matter engines, but findings like this threaten to completely rewrite the entire timeline of the cosmos.
Now, when you hear about these crises, about 5 sigma disagreements and impossible black hole stars hiding in plain sight, it's really easy to think physics is broken or that scientists have somehow failed. But it is exactly the opposite. As experimental physicist Harry Cliff notes, anomalies are the primary engines of scientific discovery. Finding out that you are dead wrong is often the only way to realize there is a deeper, more beautiful truth waiting to be uncovered. Crises aren't a reason for despair. They are the literal mechanism of progress. And honestly, the Hubble tension in these bizarre early galaxies are just the tip of the iceberg. We have other anomalies currently teetering on the edge of breaking our standard models. We've got the muon G2 experiment showing subatomic particles magnetically wobbling in ways the standard model cannot fully explain. We have the glaring asymmetry between matter and antimatter. I mean, why is there something rather than nothing? And we still have the 50-year-old, totally unresolved black hole information paradox, where quantum mechanics and general relativity just violently clash. We are sitting on the precipice of a massive paradigm shift.
Which leaves us with the ultimate question. What actually happens when our most fundamental laws of physics finally break down? From Einstein's impossible ripples finally being caught, to the elusive, frustrating ghost of dark matter, to the crisis of an expanding universe that refuses to make mathematical sense, the case file of the cosmos remains wide open. The breakdown of our laws isn't the end of the story, it's just the invitation to write the next chapter. Stay curious, keep looking at the data, and we will see you in the next explainer.